Tear open your wall. Behind the drywall sits engineered wood, either plywood or OSB oriented strand board. They look completely different yet serve identical purpose. Plywood, smooth layers of thin wood stacked like pancakes. OSB, chaotic jumble of wood strands compressed together. North American construction consumes 30 billion square feet annually, enough to cover Rhode Island 50 times over. One panel costs $12. The house surrounding you required 300 panels minimum. How does round tree trunk become flat sheet stronger than solid wood? Why did ugly OSB nearly kill beautiful plywood? Stay with us. You'll witness the violent beauty of spinning logs becoming continuous wood ribbons and discover the counterintuitive secret. Wood is stronger when you destroy its natural structure. The mill dominates the landscape, a facility processing 1 million board feet daily. Log trucks arrive continuously, each hauling 40 tons of Douglas fir or southern yellow pine. The debarking drum, 60 feet long and 10 feet diameter, rotates like giant clothes dryer. Logs tumble inside while high-pressure water jets at 3,000 psi blast bark away. The noise resembles continuous explosion. Workers wear double hearing protection. Watch the veneer lathe operation. A peeler lathe grips 8-foot logs at both ends, spinning them at 200 RPM while a knife blade, sharp as surgical scalpel and wide as the log, shaves continuous ribbon of wood. The veneer peels off like paper towel unrolling, emerging as sheet 1/8 inch thick and hundreds of feet long. 20 workers monitor 12 lathes simultaneously. One operator explains, "Log spins, knife stays still. Physics does the work. We just remove what breaks." The veneer ribbon, still damp from trees' moisture, feeds through dryers. Conveyor ovens stretching 300 feet. Temperature reaches 350 degrees, reducing moisture from 50% to 6% in 8 minutes. Dry too fast, the veneer cracks. Too slow, production bottlenecks. Sensors monitor moisture content constantly, adjusting heat and speed automatically. After drying, veneer gets clipped into precise sheets, 4 feet by 8 feet, the industry standard. Automated clippers cut at speeds exceeding 1 sheet per second. The clipping produces massive waste. 30% of veneer becomes scraps. But nothing wastes here. Those scraps feed directly to the OSB plant next door. The integration is complete. Plywood's waste becomes OSB's raw material. One tree enters, 2 products exit. Glue application transforms loose veneer into plywood through chemistry. Phenol formaldehyde resin, waterproof adhesive surviving decades of weather exposure, gets sprayed onto veneer surfaces. The glue spreads microscopically thin, just 0.02 of an inch. Too much glue costs money and creates brittle joints. Too little, the plywood delaminates under stress. The layup process stacks veneers perpendicular to each other, grain directions alternating 90 degrees between layers. This cross-grain construction is plywood's genius. Solid wood splits easily along grain but resists splitting across grain. By alternating grain directions, plywood eliminates directional weakness. A 5-ply panel, 5 layers total, achieves strength in all directions that solid wood can't match. The stacked sheets, still unbonded, go to the press. The hot press is where plywood is born. Massive hydraulic press, 40 feet square, contains 30 openings stacked vertically. Each opening holds 20 plywood panels. Workers load 600 panels simultaneously, 12,000 square feet entering press at once. The platens close, applying 1,000 psi pressure while heating to 290 degrees. Under heat and pressure, the phenolic resin undergoes chemical cross-linking, molecular chains bonding permanently. The process is irreversible. Once cured, the glue can't melt again. Press time varies by thickness. 3 minutes for 1/4 inch, 12 minutes for 3/4 inch. When press opens, steam erupts as residual moisture flashes. The panels emerge hot, rigid, transformed. What entered as loose layers exits as single engineered unit, stronger than the tree it came from. OSB manufacturing begins differently, with destruction. Instead of peeling veneer, trees get shredded. The strander machine uses rotating disc containing hundreds of knives. Logs feed through, emerging as strands. Thin rectangles 6 inches long, 1 inch wide, 0.025 inches thick. The violence is spectacular. logs disintegrating into thousands of pieces in seconds. These strands dry similarly to veneer but require less precision. Moisture content targets 8%. The dried strands get coated with wax and resin, different chemistry than plywood. OSB uses MDI, methylene diphenyl diisoxygenate, bonding faster and cheaper than phenolic. The coated strands look like wood chips covered in syrup. They feed to forming stations where magic happens. Orientation. Orientation differentiates OSB from random particle board. The forming line uses electrostatic alignment or mechanical orientation systems, forcing strands to lay parallel in outer layers, perpendicular in core layer. This mimics plywood's cross-grain structure but achieves it through chaos rather than precision. Picture billions of wood strands, each finding its place in three-dimensional puzzle. The matte, loose collection of oriented strands 8 inches thick enters continuous press. Unlike plywood's batch press, OSB uses continuous process. The mat feeds into press heated to 400 degrees under 2000 psi pressure. As it travels through, thickness compresses from 8 inches to 7/16 inch while resin cures. The panel exits as continuous ribbon, cut to length by flying saws. Production speed reaches 600 feet per minute, one 4x8 panel every 8 seconds. Plywood originated in ancient Egypt. Archaeologists found plywood furniture in King Tutankhamun's tomb from 1300 BC. Modern plywood production began in 1865 when Emmanuel Nobel, father of Alfred Nobel, developed rotary lathe cutting continuous veneer. World War II accelerated development. Plywood construction enabled mosquito bombers, proving engineered wood could replace scarce aluminum. OSB emerged in 1960s Canada as solution to log supply crisis. Small diameter trees and branches, unsuitable for veneer peeling, worked perfectly as strands. Armin Elmendorf at Elmendorf Research created first commercial OSB in 1978. Initially dismissed as cheap substitute, OSB gradually proved equal or superior performance at lower cost. Today, OSB outsells plywood 3-to-1 in North American construction. The ugly duckling became the swan. Carbon emissions comparison favors engineered wood dramatically. Producing plywood or OSB generates 80% less CO2 than steel framing equivalents. Both products sequester carbon. The wood stores atmospheric CO2 for the building's lifetime. Industry plants 3 trees for every one harvested, making this genuinely renewable material. Here's the secret we promised. OSB dominates because it's democratized wood. Plywood requires perfect logs, large diameter, straight grain, minimal knots. Only 15% of logs qualify. OSB uses everything: crooked trees, small diameter, branches, plywood scraps. The random strand orientation means defects disappear into aggregate. That gnarly branch causing plywood failure becomes invisible in OSB's chaos. We learned that destroying wood's structure, cutting it into strands and reassembling randomly, creates stronger, more consistent product than respecting original form. From forest to framing, the cycle completes. We've engineered materials stronger than nature, provided by accepting that perfection comes through controlled destruction. That wall surrounding you isn't wood anymore, it's wood reimagined. It's fibers oriented and bonded beyond biological limits. Plywood taught us to slice and stack. OSB taught us to shred and randomize. Both taught us that human engineering can improve on millions of years of evolution when we stop trying to preserve what nature made and start rebuilding it our way.
A machine capable of squeezing metal like it's alive, not melting it, not breaking it, but forcing it to flow under pressure that's impossible to imagine. 80,000 tons of force concentrated at a single point. That's more than the weight of an entire army of tanks stacked on top of each other. But why does humanity need such inhumane power? And why is this giant hidden deep underground, as if they're deliberately trying to keep it out of sight? Under this press, they're not just making metal parts, they're forming the heart of airplanes, rockets, and reactors without a single welded seam. But there's one fact almost never discussed publicly. If you watch till the end, you'll understand why this press isn't an engineering marvel, but a tool of global dominance. How much is 80,000 tons? Just to put that in perspective, that's the equivalent weight of 80,000 cars compressed into a single point, or the pressure created by an entire army of giant elephants stacked on top of each other. This metal colossus, installed in 2013, is the world's most powerful forging press, surpassing all previous achievements. It's a true giant, reaching the height of a 10-story building. Its foundation is buried deep in the ground, while its upper section rises into the sky like an industrial skyscraper. It looks like a machine from a science fiction movie, but it's absolutely real and performs its incredible work every single day. This press is designed for stamping extraordinarily large and complex parts that are critically important for the aviation, aerospace, and energy industries. These can be massive panels for rocket bodies, huge wing or fuselage components for aircraft, turbine parts for power plants, or even reactor equipment. The story of these giant presses is its own epic saga, deeply intertwined with the Cold War era. Back when the USA and USSR were competing for dominance in the space race and military industry, there arose a need for super strong, seamless metal structures. The Americans were first to build presses with a capacity of 50,000 tons, allowing them to create large aircraft components without welds, drastically improving reliability. The Soviet Union wasted no time responding, creating an even more powerful 75,000-ton press that also became a legend of engineering ingenuity. These titans of their time represented the pinnacle of metallurgical technology, symbols of engineering superiority and the industrial might of superpowers. They were true monsters, capable of shaping metal with such force it seemed almost impossible. But this modern Chinese press shattered all those records, surpassing even the Soviet giant. It can crush metal with literally superhuman force. Under this press, red-hot metal blanks weighing hundreds of tons, that's like dozens of trucks compressed into a single chunk of metal, get flattened like soft clay. Metal heated to a red or yellow glow undergoes incredible pressure. It doesn't just deform, it flows under this colossal force, slowly but relentlessly taking on the required pre-designed shape. This isn't casting, this is forging, a process that strengthens the metal structure, making it denser and stronger than any cast piece. This ability to produce solid forgings of enormous size is the main advantage and defining characteristic of such presses. Picture this. You can get a massive spar for an aircraft wing or a reactor vessel component without a single weld. Weld seams, no matter how high quality they are, will always be potential weak points in metal structures. They can be sites of stress concentration, cracks, or corrosion. In mission-critical components, where the cost of failure can be catastrophic, say in an aircraft at 33,000 feet, or in a space rocket, the absence of weld seams isn't just desirable, it's absolutely essential. Solid forgings, formed under such pressure, have unmatched strength, uniform structure, and maximum reliability. They're the foundation for building supersonic aircraft, ultra-powerful rockets, spacecraft, and safe nuclear reactors. To install a press of this magnitude, you don't just build a foundation, you build an entire underground iceberg. The main structure of the press is buried deep in the earth because the enormous forces acting during forging create incredible vibrations that need to be absorbed. It's like building a foundation for a skyscraper, but in reverse, plunging into the depths of the earth for dozens of feet. Installing equipment like this is a more complex logistical operation than launching a space rocket. Press components arrive on site by the hundreds, then get assembled using giant cranes and engineering teams working for years. By the way, an 80,000-ton press force isn't just pressure, it's a controlled transformation of material at the micro level. Under that kind of force, the metal's crystalline structure changes. Grains become finer and denser, giving it exceptional mechanical properties. It's like leveling up metal to maximum stats. Here's another thing. Running a giant like this takes a colossal amount of energy. This isn't just plug it into an outlet. Powering the hydraulic pumps and maintaining stable pressure requires a dedicated power plant.
And the cooling systems that carry heat away from the hydraulic fluid, just as critical. Under these loads, the oil can get seriously hot. It's a true engineering ecosystem where every single component is mission critical for the entire complex to function. As we mentioned, instead of welding together dozens of small metal sheets, the press can forge a significant portion of the shell from a single block of metal. This makes the structure lighter, stronger, and far more resistant to fatigue. While the press doesn't stamp out tiny turbine blades, it can form large casing components for jet engines, parts that withstand extreme pressure and temperature.
Beyond aerospace, where every single pound and every hairline crack can spell disaster, this press also stamps out components for nuclear and thermal power plants. We're talking ultra-high-strength reactor housings and lids, turbine elements, generators, and other equipment operating under extreme pressure, temperature, and radiation. Here, integrity and zero defects aren't just about efficiency, they're about protecting entire regions. They also forge shafts and rotors for massive ships and industrial machinery. Enormous turbine installations on ocean-going vessels or in power generation require ultra-strong shafts that can handle colossal rotational forces and torsional loads. Forgings made under this press are perfectly suited for these purposes.
Every second, factories worldwide produce carbon fiber threads 10 times stronger than steel, yet 5 times lighter. Picture this. A strand thinner than human hair supports weights exceeding 400 pounds, more than 2 adult humans hanging from a thread, invisible at arm's length. These black filaments, woven into composites, form invisible to radar bombers, Formula One monocoques surviving 200-mile-per-hour crashes, and prosthetic limbs outperforming natural bone. How does ordinary plastic transform into material stronger than steel through fire? Why do engineers call carbon fiber the black aluminum, revolutionizing everything from spacecraft to tennis rackets? Stick around till the end. You'll discover the jaw-dropping reason carbon fiber doesn't break like metal but unravels like fabric, why recycling it became a technological arms race, and the shocking truth about what happens inside furnaces hotter than volcanic lava when atoms reorganize into crystalline perfection.
The story begins with polyacrylonitrile, pan fiber, the plastic precursor looking like white cotton thread. Massive spinning machines standing 3 stories tall in climate-controlled facilities extrude molten pan through spinnerets containing 50,000 microscopic holes. Each hole, measuring 3/10,000ths of an inch across, thinner than blood cells, produces one continuous filament. Picture spider silk production scaled to industrial extremes. These filaments emerge at speeds reaching 3,000 feet per minute, fast enough to cross football fields in seconds. Chemical baths stretch the fibers, aligning polymer chains parallel to fiber length. This molecular orientation determines everything. Randomly oriented polymers create weak thread. Aligned chains create strength rivaling steel. Workers monitor tension constantly. Variations of 2% cause inconsistent properties requiring entire batches, thousands of pounds worth, to be scrapped. The pan production facility operates 24/7, producing 50 tons daily, enough fiber to circle Earth's equator if laid end to end. Next comes oxidation, the first transformation where chemistry becomes alchemy. Massive ovens, stretching 200 feet long like horizontal tunnels, heat pan fibers to 500 degrees Fahrenheit in pure oxygen atmosphere. Inside these furnaces, oxygen atoms attack carbon-hydrogen bonds in the polymer backbone. Hydrogen burns away as water vapor, leaving behind carbon-nitrogen ladder structures stabilized through cross-linking. This stabilization process takes 90 minutes as fibers crawl through ovens on tensioned rollers. Temperature control matters critically. Too hot, fibers ignite catastrophically. Too cold, cross-linking remains incomplete, causing failure during subsequent heating. The oxidation chamber maintains oxygen concentration at 23% with tolerance of 0.5%. Operators monitor fiber color constantly, watching white pan transform through yellow to dark brown. That color change represents chemical metamorphosis, polymer becoming something fundamentally different, no longer meltable, now heat-resistant enough to survive temperatures that vaporize aluminum. Giant carbonization furnaces, operating at temperatures exceeding 3,000 degrees Fahrenheit, complete the transformation. These aren't ordinary ovens, they're inert atmosphere chambers purged with nitrogen gas, creating environments where oxygen molecules cannot exist. Inside this oxygen-free inferno, stabilized fibers lose nitrogen, hydrogen, and other non-carbon elements through thermal decomposition. Only carbon remains, reorganizing into graphite-like crystalline structures. The process occurs in stages. First, furnaces heat fibers to 2,700 degrees, driving off 90% of non-carbon atoms. The fiber shrinks 25%, density increasing as material compacts. Second stage furnaces push temperatures to 4,000 degrees for graphitization, the process aligning carbon atoms into perfect hexagonal sheets stacked like microscopic playing cards. This crystalline perfection gives carbon fiber its extraordinary properties. Processing takes 3 hours, crawling through furnace sections totaling 1,000 feet long. One power interruption, one oxygen leak, and fibers oxidize catastrophically, burning like magnesium flares, destroying millions in equipment. Now comes surface treatment, electrolytic oxidation creating reactive sites for resin bonding. The carbon fiber, now black as obsidian and measuring just 0.003 inches diameter, passes through electrolyte baths while electric current flows through it. This electrochemical attack roughens the fiber surface at nanometer scale, creating anchor points where epoxy resins chemically bond. Picture this: untreated carbon fiber in epoxy resin slides apart like oiled rope, strong individually but weak as composite. Surface-treated fiber bonds molecularly to resin, creating integrated structure where fiber and matrix function as single material. Modern aerospace composites achieve interface strengths exceeding 12,000 pounds per square inch, meaning the bond between fiber and resin is stronger than many metals themselves. This step is critical because composite strength depends not just on fiber properties, but on load transfer efficiency from matrix to fiber. Poor surface treatment causes delamination, layers separating under stress, the characteristic failure mode making carbon composites unravel rather than fracture. The sizing application follows, coating fibers with protective polymer layer. Massive rollers submerge fiber tows, bundles containing 12,000 individual filaments, through sizing baths containing proprietary polymer formulations. This coating serves triple purpose: protects fibers during handling, improves resin wetting during composite layup, and provides limited abrasion resistance. Workers wind treated fiber onto spools holding 10 miles of continuous filament. These spools, weighing 200 pounds each, ship to composite manufacturers worldwide. Quality control inspects random samples continuously. Tensile testing machines pull individual fibers until failure, measuring breaking strength, elastic modulus, and elongation. Modern aerospace-grade carbon fiber withstands stresses exceeding 800,000 pounds per square inch, 50 times stronger than structural steel. The fiber stretches only 1.5% before breaking. Steel deforms 300% more. That limited elongation explains why carbon structures crack suddenly rather than bending. No warning, just instantaneous failure when stress exceeds capacity. After arriving at composite manufacturers, fibers get woven into fabrics or used as unidirectional tapes. Automated looms, programmed like textile machines but operating at glacial speeds to prevent fiber damage, weave intricate patterns. Plain weave creates checkerboard appearance, twill weave produces diagonal patterns, satin weave maximizes smoothness for aerodynamic surfaces. Each weave pattern offers different mechanical properties. Engineers select patterns matching stress directions. Picture this. Laying up carbon composite resembles origami, with materials costing $300 per pound. Technicians cut fabric patterns, stacking layers in precise orientations. Each ply orientation, 0 degrees, 45 degrees, 90 degrees, contributes specific strength characteristics. A typical aerospace laminate contains 40 plies, each 0.005 inches thick, creating structures 8 inches thick, yet lighter than equivalent aluminum. Between each ply, workers brush epoxy resin, ensuring complete fiber wetting. Air bubbles trapped between layers become stress concentrators, causing catastrophic failure. So layup occurs in clean rooms, maintaining air purity rivaling semiconductor fabs. Curing transforms wet layup into solid composite through heat and pressure. Massive autoclaves, pressure vessels 30 feet in diameter and 100 feet long, create environments combining 300 degrees Fahrenheit and 100 psi pressure. Inside these industrial pressure cookers, epoxy resin chemically cross-links while pressure squeezes out excess resin and air voids, compacting layers into dense laminates. The cure cycle takes 8 hours following computer-controlled temperature and pressure ramps. Heat too fast, resin boils, creating voids. Heat too slow, productivity plummets. Modern autoclaves monitor 200 sensors simultaneously, adjusting conditions to within 1 degree and 0.5 psi. After curing, parts exit as rigid structures, material properties now locked permanently. Non-destructive testing using ultrasound and X-rays searches for defects. Even microscopic voids or delaminations require part rejection because carbon composites tolerate 0 defects. Unlike metals tolerating small cracks through ductility, carbon composites fail catastrophically once cracks initiate. That brittleness demands perfection during manufacturing. This technology emerged from 1960 space race. Thomas Edison experimented with carbon filaments in 1880s for light bulbs. But modern carbon fiber originated when British researcher William Watt developed pan-based process in 1963 at Royal Aircraft Establishment. The breakthrough enabled high-strength fibers commercially viable. Formula One adopted carbon fiber in 1981 when McLaren built the first composite monocoque chassis. Driver John Watson walked away from a 200-mile-per-hour crash at Monza, the carbon tub protecting him despite complete car disintegration. That demonstration convinced aerospace industry. Boeing's 787 Dreamliner, entering service in 2011, uses 50% composite materials by weight. Wings, fuselage sections, tail, slashing fuel consumption 20% versus aluminum equivalents. The B-2 Spirit stealth bomber, revealed in 1989, incorporates carbon composites extensively. The radar-transparent properties, combined with geometric shaping, create aircraft virtually invisible to detection. Today, carbon fiber production exceeds 120,000 tons annually, growing 15% yearly as industries discover applications from wind turbine blades to bicycle frames. Carbon emissions drop by 32% when using carbon fiber in aircraft versus aluminum. Lighter structures require less fuel over millions of flight miles. Industry saves over $68 billion annually through weight reduction in transportation. Wind turbines using carbon fiber blades generate 18% more electricity through longer, lighter blades, impossible with fiberglass. So here's the secret promised. Carbon fiber doesn't break, it delaminates. Unlike metal fracturing through crack propagation, carbon composites fail through layer separation. Impact damage creates barely visible surface dimples, hiding extensive internal delamination, while composites require ultrasonic inspection after any impact. That failure mode makes recycling challenging. You can't melt carbon fiber like aluminum. Heating destroys the crystalline structure that provides strength. Current recycling uses pyrolysis, heating composites to 1,000 degrees in oxygen-free environments, burning away resin while preserving fibers. Recovered fibers retain 70% of original strength, creating secondary markets. From plastic thread to aerospace revolution, cycle completes. Carbon fiber represents humanity's ability to reorganize matter at atomic level, creating materials nature never intended. We've learned to cook polymers in furnaces hotter than volcanoes, aligning carbon atoms into crystalline perfection, stronger than any metal, yet lighter than water. That thread, thinner than hair, doesn't just reduce weight. It enables impossible structures. Aircraft wings spanning 200 feet without internal support. Prosthetics stronger than bone. Spacecraft components surviving forces that pulverize steel. We've engineered the future, one microscopic fiber at a time.
Every year, over 100,000 kilometers of new rails are laid across the planet. And every single one of them goes through hell first. Fire over 1,500 degrees, the crushing force of rollers, and jets of water that cut metal like glass. From scrap heap to gleaming steel, a rail's journey is like an initiation, where every step decides whether it survives or shatters under the first train. But what makes this steel so perfect that it can handle thousands of tons of pressure every day without bending or cracking? Stick around, and you'll see how the arteries that move the entire world are born. First, you gotta make the steel. A mix of scrap metal, iron ore, coke, and limestone gets dumped into the furnace, the raw ingredients for a future rail. The temperature in the blast furnace hits over 2,700 degrees Fahrenheit. That's 1,500 Celsius. Under that hellish heat, the metal turns liquid, glowing like the sun. Workers keep a close eye on the composition. Even an extra 0.1% of carbon can make the rail too brittle or too soft. After melting, the molten steel is poured into molds, metal forms that create rectangular blocks called ingots or slabs. They don't look like a rail yet, just solid bars a few meters long and over a foot wide. After pouring, each blank is cooled, but not completely. It's kept warm to reduce stress during the rolling process. This stage is the foundation for everything. If the steel comes out bad, even a perfect rolling job won't save it. So quality control here is almost a ritual. Chemists check the composition, metallurgists monitor the temperature, and automatic sensors track the cooling uniformity. Only when every single parameter is locked in does the blank move on into the fiery heart of the rolling mill. In the rolling mill, massive billets, up to 20 meters long, are heated in furnaces to over 2,200 degrees Fahrenheit, 1,200 Celsius. The metal becomes pliable, like dough, but keeps its density and strength. The hot blank is immediately fed into reversing rolling stands. These are huge machines with heavy rollers. It passes through them several times, first to reduce its thickness, then to give it the right shape. Each pass is a squeeze and stretch, gradually transforming the metal from a simple billet into a future rail with its complex profile: the head, the web, and the foot. To get the exact geometry, they use a final sizing roll. It's like the final polish of the shape, with tolerances on this step not exceeding 0.3 of a millimeter. Right after rolling, while the rails are still hot, they go through a cooling process. They're either evenly blasted with air or left to cool on an open rack. It's crucial that the cooling is symmetrical. Otherwise, the metal could warp. To ensure a smooth, bump-free ride at high speed, individual rails are welded into long sections, up to 400 meters without a single joint. The main method is thermite welding. In a special mold between two rails, a gap of a few millimeters is left. A molten steel mixture, created by the reaction of powdered aluminum with iron oxide, is poured in. The temperature hits a scorching 4,500 degrees Fahrenheit, 2,500 Celsius. This molten metal flows into both parts of the rail and fills the joint area. When it solidifies, it creates a monolithic bond, stronger than the rail itself. After that, the excess metal is trimmed off, and the weld is ground down to a perfectly smooth level, without a single bump. Every joint is inspected, with ultrasound or eddy currents, to make sure there are no hidden micro cracks. These long rails are easier to transport than you'd think. They're either wound onto special drums or carried on platforms with pivoting supports. And on the construction site, the sections are joined again, this time by welding or using special bolted joints. The result is a continuous rail line that stretches for kilometers without a single click. The same silent glide we've come to expect on high-speed trains. But first, after rolling and welding, the rails are still alive. There's stress left inside the metal, and the grain structure needs to be stabilized. This is where heat treatment comes in, giving the rail its strength, wear resistance, and durability. And it looks almost like a metallurgical spa session. The rail is rapidly heated to high temperatures, around 1800 degrees Fahrenheit, 1000 Celsius. This is done in furnaces, tens of meters long, where the temperature is controlled to the degree. At this heat, the steel's crystal lattice shifts into a new state, austenite. But the main event starts after that. The rail is instantly cooled. Jets of high-pressure water are aimed along the head and web, the very parts the wheel rolls on. The temperature drops in a flash, and a new structure forms in the metal, martensite, an extremely hard, wear-resistant phase. But to avoid brittleness, the rail is slowly heated and cooled one more time. This balances the structure, relieves any extra internal stress, and ensures the rail can handle frost, heat, and thousands of trains a day. In the end, the metal holds its shape and withstands pressures of tens of tons per square inch without deforming. Before a rail hits the road, it goes through a whole series of tough tests, like it's trying to join an army of high-speed transport. In special labs, it's checked for strength, hardness, geometry, and internal defects. First up, ultrasonic testing. High-frequency waves are sent into the rail. If there's a microcrack or void inside, the signal bounces back and flags the problem. Then, hardness measurements along its entire length to make sure the heat treatment was uniform. At the same time, its straightness and profile are checked. Laser sensors scan every inch, detecting even tiny warps that could cause vibration or wear. And finally, bend and impact tests. A piece of the rail is loaded with pressure dozens of times greater than the weight of a train to make sure it can handle any challenge on the route. When the rail has successfully passed all the tests, it's time for its most important journey, to the installation site. But how do you transport giant metal strips over 90 meters long? Regular trucks can't handle it. Here, they use special railway platforms with curved supports that reduce stress and prevent the rail from sagging or vibrating during transit. Sometimes, rails are transported already welded into even longer sections, from 400 to 600 meters. Before installation, the rails are heated or cooled depending on the ambient temperature. This is to compensate for the thermal expansion and contraction of the metal. Otherwise, it would buckle in the heat or gaps would form in the cold. In practice, each rail is laid with these physical changes in mind, usually at a stress-free temperature point. Then there are two paths, either long-term dry storage in double-walled concrete containers or reprocessing. That happens in other countries, as the US mostly stores rather than reprocesses. In dry storage, the assemblies stand for decades, cooled by natural ventilation, as if in a nuclear monastery. This isn't the end, but a new stage of life, slow, controlled, but deeply connected to the future of energy. Because even after the reactor, this fuel remains a source of heat, a lesson, and a reason for respect. Transportation is under guard on a special route with an escort, GPS, and mandatory 2 seals, 3 codes, and a dosimeter on every side. Because even in its peaceful form, this is dangerous stuff that commands respect. After all is said and done, what's left is the depleted uranium hexafluoride. They call it tails. It's a mix of isotopes that still has a little U-235, but not much. These tails are stored in steel barrels, in special supervised yards. But in the future, they could be reprocessed in next-generation reactors, squeezing out every last drop. When a fuel assembly has served its 4 or 6 years in the heart of a reactor, it's no longer the shiny star it was at launch. It's removed, carefully by a robotic system, and moved into pools of water. The depth is over 20 feet. The water cools it and shields the radiation because the fuel is still hot, both physically and radioactively. There it rests for several years. Next, the pellets are sintered in furnaces at almost 3,000 degrees to make them as strong as porcelain. Then they're polished and ground. Perfect dimensions are crucial for a tight fit inside the cladding. The pellets are loaded into long metal tubes. Fuel rods, usually made of a zirconium alloy because it doesn't rust, doesn't react with water, and can withstand insane radiation. Each rod holds over 300 pellets. The rods are hermetically welded shut and bundled into modules, fuel assemblies. They look like a frame of several dozen tubes gathered into a square. One such assembly can weigh over 1,500 pounds and works for up to 6 years in a reactor. After assembly comes testing for leaks, uniform filling, weld integrity, and behavior under temperature. There are no small details, because any one of them could cost not just money, but lives. The finished fuel is packed into armored containers that can withstand impacts, fires, and falls from a height. But one centrifuge isn't enough, so they're connected in cascades of hundreds, sometimes thousands. Each one slightly enriches the gas, then passes it to the next. And so it goes, cycle after cycle, until the U-235 content reaches at least 3 or 5%. That's the reactor-grade standard. For weapons, of course, they follow entirely different routes, which are classified and under strict international control. Okay, the gas is enriched, but you can't feed a reactor with a gas. So now it's converted again, this time into a solid ceramic form. After a series of chemical reactions with hydrogen, oxygen, and ammonia, the gas becomes uranium dioxide, a solid substance with a dark gray color. This powder is pressed under 20 tons of pressure into small cylindrical pellets, 3/10 of an inch in diameter. They look almost cute. But each of these little pills holds an energy equivalent to 17,000 cubic feet of natural gas. And so, mission accomplished. The dust has been turned into a gas, ready for the most interesting part, isotope enrichment. But don't get too excited yet. This gas is like a wild cobra. Beautiful, shiny, but if it bites, no one can save you. You think a washing machine spins fast? You haven't seen nuclear centrifuges that do 70,000 revs a minute. That's 10 times faster than a jet engine turbine. And all for one thing: to separate uranium isotopes. Uranium hexafluoride, that same toxic gas we just made, is pumped into a tall, narrow cylindrical chamber, which is spun up to an insane speed. Centrifugal force does its thing. The heavier U-238 atoms are flung to the edge, while the lighter U-235 atoms stay closer to the center. A tiny microscopic difference, 1% in mass, and all this explosive technology spins just for that. That means you just need to heat it a little, and it turns from crystals into vapor. But it's not that simple. It's extremely toxic. It corrodes metals, destroys skin, and in moist air, it instantly turns into hydrogen fluoride and uranic acid, basically a deadly cocktail. That's why this is all done in sealed, automated reactors that look more like devices from an evil genius's lab. Temperature, pressure, ventilation, everything is under control. Workers sit behind thick windows, watching the gauges. Any mistake, boom or hiss, and you're in a hazmat suit scrambling for the decontamination shower. This substance forms as solid whitish crystals when cooled to room temperature. These crystals are stored in steel containers, drums with engravings, batch numbers, and a radioactive sign. Each one weighs up to 14 tons. Yellowcake is packed into double-walled drums, loaded onto escorted trailers, plastered with radiation signs, and off it goes to an enrichment plant. It's from this toxic dust that the journey begins, the one that leads to the white light of a lamp over your kitchen table, or the electricity in the subway hurtling beneath New York. Right then, the yellowcake has arrived, in drums, radioactive and dry as a desert wind. The next step, turn it into a gas. And not some lavender-scented air freshener, but uranium hexafluoride, the very same stuff from which the required isotope for reactors and other things is later separated. Let's cook, baby. The uranium concentrate is first dissolved in acid, purified, filtered from impurities, converted into uranium dioxide. And this is where the magic starts. The uranium dioxide is treated with fluorine in special reactors at a temperature of 1,000 degrees. And as a result of the reaction, a volatile, transparent gas is formed, which boils at 133 degrees. The rest is mostly useless mass that doesn't work in a reactor. And to squeeze the required drop of energy from it, hundreds of tons have to be processed. That's why they say nuclear energy is quite the marathon. After mining, the ore is crushed, milled, and thrown into a chemical bath. Acid or alkaline solutions are added, which extract the uranium like coffee from a filter. Then comes filtering, precipitation, and drying at 500 degrees. And what comes out is yellowcake, a yellow powdered concentrate. The official name is natural uranium concentrate, but everyone at the plants just calls it yellowcake. It looks pretty, mustard-colored, fluffy, like a spicy powder for a Barbie. But God forbid you breathe it in or touch it. Alpha radiation, a long half-life, dangerous dust that gets into your lungs and settles there forever. It's handled only with respirators, suits, and behind 3 layers of glass shielding. It all starts in the dust. And that's not a figure of speech. Uranium ore is mined in hot, arid regions. Arizona, Wyoming, Texas, New Mexico. Think cowboy country, but instead of lassos, they have drill rigs, and instead of a sheriff, engineers in anti-radiation suits. The sun here is a scorcher, up to 100 degrees Fahrenheit in the shade if you can find any. There are 2 ways to get it. Open pit mining, where they strip the topsoil and haul the ore out with excavators, and underground mining, with explosives, lifts, and ventilation that howls like an old tractor. Then there's the in situ leaching method. Pipes are driven into the ground, special solutions are pumped in to dissolve the uranium straight from the rock, and then it's all pumped back out. All this ore, a gray-brown rock, looks no different from ordinary stone. But inside it, uranium-235 makes up only 0.7%. What could be scarier than dust that glows with an invisible light? A rock that looks like ordinary gravel, but holds the fuel for power stations that light up megacities. So why is uranium called an energy marathon? Because to get just a few grains, you have to move hundreds of tons of earth, boil ore in acids, and turn it into a yellow powder that can kill with a single touch. And this is where the real alchemy begins. Toxic dust becomes a gas, and that gas becomes energy. But there's a detail they don't talk about publicly, and you'll only find it out at the end of this video. Every year, dozens of nuclear submarines are launched into the world's waters, giants capable of diving to depths of over 2,000 feet and remaining invisible for months. These are truly underwater cities, with a reactor at their heart, hundreds of tons of steel and titanium alloy, and incredible silencing systems that absorb sound. But how is such a machine born from cold metal? What secrets does its construction process hide, where even a microscopic crack can cost lives? Watch carefully. In the finale, you will learn what is usually hidden behind the 7 locks of military archives. A nuclear submarine is a complex engineering creation, the development of which begins long before the first sheet of metal hits the machine tools. It all starts with computer-aided design. At this stage, several key parameters are considered: the size and shape of the hull, the power supply system, weaponry, and noise reduction measures. The length can range from approximately 300 to 560 feet depending on the class, and this directly affects the diving depth. The most advanced submarines can descend to 1,968 to 2,460 feet, and some experimental models, even over 3,000 feet. Based on the initial designs, physical models of the submarine are created, which are tested in special water tunnels. This helps engineers see how the hull shape affects maneuverability, water resistance, and noise level. In parallel, computer modeling allows predicting how the submarine will behave underwater at different speeds and maneuvers. After simulations, when all calculations match up, the blueprints are sent to production. This is where the most interesting part begins: the actual assembly. For the construction of nuclear submarines, special materials are used that can withstand high pressure at great depths and provide protection against corrosion. Usually, these are high-quality steel or titanium alloys. Steel is cheaper and easier to produce, and it withstands pressure and impacts well. Titanium has the advantage of high strength, lightness, corrosion resistance, and being non-magnetic, which makes it harder to detect the submarine. However, titanium is more difficult to process and weld, as its melting point is higher, about 3,092 degrees Fahrenheit, versus approximately 2,552 degrees Fahrenheit for steel. Before construction begins, the metal sheets undergo heat treatment. They are heated, rapidly cooled, and treated with special anti-corrosion compounds. The hull of a modern submarine is usually made of modular sections. This makes construction easier. Metal sheets are cut by giant laser and plasma devices with millimeter precision. Then, each sheet is bent under a press to give it the required shape. Often, some hull elements have a spherical or cylindrical structure. The sections are assembled separately. These are huge rings, or compartments, which are later joined in the final stage. This division into sections allows for working on different parts of the submarine in parallel, speeding up the construction process. When all the parts are ready, one of the most critical stages begins: welding the hull. The welds must be extremely strong. Even a microscopic crack at depth can cause a catastrophe. Therefore, automated electron beam welding is used, which allows for creating the most uniform seams possible. Additionally, each seam is checked with ultrasonic scanners and X-rays. Most nuclear submarines have a double hull. A strong inner hull withstands high pressure at great depth, while an outer hull provides a streamlined shape, improves hydrodynamics, and helps reduce the likelihood of detection. Ballast tanks, which regulate the submarine's buoyancy, are usually located between the hulls. To keep the submarine as stealthy as possible, it is covered with anechoic layers. These are polymer tiles that absorb sound waves, as well as composite materials with micropores that reduce the acoustic signature, and noise-dampening coatings applied to the propellers and power plants. When all the hull sections are ready, their joining begins. Giant cranes move the compartments into special docks, where they are connected using bolted joints and welding. Next, the hull is tested for leaks by filling it with compressed air and checking for any escape. And strength tests are conducted in a hydrostatic tank, where pressure similar to deep sea diving conditions is simulated. After assembling and checking the hull strength, the key element is installed: the nuclear reactor. This is the heart of the submarine, allowing it to stay underwater for months or even years. A nuclear reactor is not just an engine, but a whole complex of energy and auxiliary systems that occupies a significant part of the submarine. Modern nuclear submarines use reactors that operate on the principle of heating water to produce steam. The fuel, usually enriched uranium-235 or uranium-238, is located in the reactor core. During the nuclear reaction, heat is released, which heats water in a closed loop. The hot steam is directed to turbines, which generate electricity and drive the propeller. The reactor is delivered in special protective containers and installed by a crane through an upper hatch in the hull. Inside, a compartment is provided for it, surrounded by materials that minimize radiation. Emergency cooling systems and sealed barriers are also located there. The reactor is mounted on a shock-absorbing platform that reduces vibrations and impacts during the submarine's movement. Then, heat exchangers and steam generators are installed, which are responsible for the circulation of the coolant, and turbines and electric generators are mounted. The functioning of all the submarine systems depends on their operation. Finally, the reactor compartment is sealed with multi-layered lead and composite panels to protect the crew from radiation. To check the readiness of the structure, the first startup of the reactor is carried out in test mode. The power is gradually increased, the radiation level in the compartments is monitored, and the cooling systems are tested at maximum loads. When the reactor is already installed and the submarine has a fully formed hull, it is still not ready for service. Inside, there are still only empty corridors and compartments, so the next stage is the installation of control systems, life support, weaponry, and crew quarters. Sonar systems are mounted in the bow and along the hull. They track enemy ships and scan the seabed. A computer system and automated combat control stations are also installed, ensuring maneuvering accuracy. Of course, weapon systems are also mounted. Torpedo tubes are located in the front part of the submarine, and they usually have automated reloading mechanisms for quick preparation of new shots. On strategic submarines, missile silos with hydraulic locks and pressure control systems are installed in the central part, which allow for launching missiles even at great depths. Since the crew can spend months underwater, the submarine must be as autonomous as possible. For this, nuclear submarines are equipped with oxygen generation systems, carbon dioxide removal, heating, ventilation, and a sufficient supply of water. If you've seen capsule hotels, then inside a submarine, there is something similar: sleeping capsules for the crew to rest. In addition, there are dining areas with significant food supplies and a command center with control panels, maps, and communication equipment. After arranging the living area, the submarine is almost ready to go to sea, but a series of complex tests are still ahead, which must prove that it can withstand colossal pressure, remain inconspicuous, and is maneuverable in extreme conditions and capable of performing combat missions. Such checks last from 6 months to 2 years and include both factory testing and combat training for the crew. First, the submarine is checked again for leaks. All electrical and navigation systems are tested, and the reactor is started up again. After this, the submarine goes to the open sea for the first time, where stabilizers, hydraulic cylinders, and steering mechanisms are checked. Sharp turns, dives, emergency maneuvers are practiced, and the maximum speed is determined, usually 25 to 35 knots, which is about 29 to 40 miles per hour. Then the submarine descends to periscope depth, about 65 feet, to assess stability. At greater depths, the operation of the ballast tanks under load is checked, and the submarine is gradually brought to its maximum permissible depth, which is about 1,968 feet, depending on the class. The reactor is necessarily tested under maximum load. When the submarine confirms its seaworthiness and reliability, they move on to testing the combat systems. The first shots are usually performed with training torpedoes, without a warhead. On strategic submarines, a launch of one ballistic missile may be conducted with a launch-dive-disarm in the air trajectory. On tactical submarines, the launch of cruise missiles like the Tomahawk or its analogs is checked. In addition, the submarine enters a special zone with hydroacoustic sensors, where specialists measure the noise level at different speeds and check the effectiveness of the noise-dampening coating. Finally, the submarine undergoes a simulated combat mission, during which the crew demonstrates its readiness for real service. Every year, over 150 million cubic meters of plywood are produced worldwide, a volume that could circle the Earth several times in train cars. But few people stop to think that behind this lies a unique technology where wood is literally unrolled into a continuous ribbon and then assembled into a super strong material that can withstand colossal loads. How do ordinary logs, after spa treatments in giant pools and a dance with knives, turn into perfectly smooth sheets, ready to serve in furniture, ships, and even skyscrapers? Watch until the end, and you'll discover one hidden secret of this production that isn't talked about publicly. It all starts in the forest, where the best specimens are selected for plywood production. You need perfectly straight, cylindrical trunks without a large number of knots or defects, preferably from birch, alder, pine, or other species. After being delivered to the factory, the logs go through the first and very important stage of preparation hydrothermal treatment. They are submerged in giant pools of hot water, where they spend several hours, and sometimes up to a day. This sort of spa for logs has a purely practical purpose. The hot water softens the wood, making it more plastic and pliable. Without this, further processing would be impossible, as cold wood would simply crumble and break. After their bath, the logs are fed to a line where their bark is stripped off. Special machines quickly and efficiently clean the trunk, leaving a smooth, light surface. Then the logs are sawn into standard lengths, ready for the main stage of transformation. The heart of the entire plywood production process is the peeling lathe. This is where something incredible happens, something that contradicts our usual understanding of wood processing. The prepared log, clamped at both ends, begins to rotate at a huge speed around its axis. A long, razor-sharp knife, installed parallel to the axis of rotation, is slowly brought towards it. As it cuts into the wood, it begins to peel off not shavings, but a continuous, seamless ribbon, just 1 or 2 millimeters thick. It's like unrolling a giant roll of paper towels. The machine literally unrolls the trunk, like a scroll of ancient papyrus, turning a 3-dimensional cylinder into a flat, long ribbon. This ribbon is called veneer. The long sheet of veneer moves further down the conveyor, where giant clippers chop it into sheets of standard size. All that's left of the log is a thin central cylinder, the so-called pencil, which is then used for other purposes. Freshly made veneer contains a lot of moisture, which is an enemy of the strength and stability of the future plywood. Therefore, the next mandatory stage is drying. The veneer sheets are fed into long, multi-tiered drying chambers. Inside them, as if on the shelves of a giant cabinet, the sheets slowly move on a conveyor, while hot air intensely blows on them from all sides. The temperature and speed of the air are strictly controlled to dry the veneer evenly and avoid cracking or warping. In a few minutes, the damp and flexible sheets turn into light, slightly brittle, and perfectly dry blanks, ready for gluing. At this stage, the dried veneer sheets are sorted by quality. Then they pass through a glue spreading machine. Special rollers, dipped in a bath of synthetic glue, usually based on phenol formaldehyde or urea resins, apply a uniform, sticky film to one side of every other sheet. Next begins the process of forming the layup. A dry sheet of veneer is placed on a table. On top of it, a sheet coated with glue is placed. And here lies the main secret. Each subsequent sheet of veneer is laid so that the direction of its grain is perpendicular to the previous one. If the first sheet's grain runs lengthwise, then the second's runs crosswise, the third's lengthwise again, and so on. This cross-grain structure is the key to plywood's strength. It paralyzes the wood's natural tendency to split along the grain and evenly distributes the load over the entire area of the sheet. That's why plywood is equally strong in all directions. The number of layers in the layup is always odd, so that the structure is symmetrical, and the outer layers have the same grain direction. The formed layups of veneer are fed to the most powerful section of production, the hot press. This is a giant multi-level structure, between whose plates several dozen future plywood sheets are loaded simultaneously. When the press is loaded, the plates begin to close. With an enormous force, reaching tens of kilograms per square centimeter, the plates compress the veneer layups, turning them into dense, thin blocks. At the same time, the plates are heated to a temperature of 302 degrees Fahrenheit. Under the influence of high pressure and temperature, the glue polymerizes, penetrating into the pores of the wood and permanently bonding the layers into a single, incredibly strong monolith. The pressing process lasts for several minutes, after which a finished plywood board is born. Hot sheets of plywood come out from under the press and are stacked for gradual cooling. This is important to avoid internal stresses in the material. After cooling, the sheets undergo final processing. Powerful circular saws trim the edges, giving the sheets precise geometric dimensions. Then comes sanding. The sheets pass through sanding machines with endless abrasive belts, which make their surface perfectly smooth and even. After this, each sheet undergoes strict quality control. Inspectors check it for defects, delaminations, knots, cracks, glue spots. Depending on the surface quality, the plywood is assigned a certain grade, and a corresponding marking is applied to it. The finished, sorted, and packaged stacks of plywood are sent to the warehouse, to later become part of furniture, houses, ships, and countless other structures, demonstrating to the whole world how human intellect can improve upon nature itself. The global scale of production is also impressive. Annually, over 150 million cubic meters of plywood are produced worldwide. If you were to load all of this quantity into railway cars, the resulting train would circle our planet at the equator several times. The pencil that remains after peeling the veneer is a vivid example of how modern production strives for maximum waste-free efficiency. It is not waste, but a valuable raw material for which there are several clearly defined paths. Its future fate depends on the thickness and quality of the wood. If the cylinder is massive enough, it is sent to a sawing line, where it gets a second life in the form of lumber. Small boards and bars are cut from it, which are ideal for creating the invisible but strong frames for sofas and armchairs, legs for chairs, elements of children's beds, or wooden pallets.